Okay, so welcome everybody to Impact 2022, which is organized by Aligarh Muslim University. And I'm going to talk about low energy CMOS mixed signal circuits from auto-calibrated sensing to computation. The reason I chose this topic was I wanted to give you a kind of may I request to mute because I can hear echo of my voice. Yeah, so I request to please mute your mic. I think conference also needs to mute. Conference organizers, yeah, thank you. Okay, so the reason I chose this topic was I wanted to give you a glimpse of these areas, which is very important for in today's technologies and the applications. Specifically, the need comes from applications point of view, and also towards the direction which takes care of which takes advantage of, in fact, the existing platform technologies. In fact, everything is driven by how much technology can give us and how much we can build upon that. I'm also giving this talk as a part of the distinguished lecture talk because in IEEE Sensor Council, I noticed also Impact 2022 is eventually supported by 2 chapters of IEEE in India and US. So therefore, this also comes under that distinguished lecture talk because it's all about areas related to sensors, which is one of my active areas at present. So when we talk about, or we want to talk about a keynote talk. So the question is that what would be a keynote talk? A keynote talk should bring various graphs and say that what is the trend, what is increasing, what is decreasing, what will happen, what is predicted to happen, and so on. More often, I think that this kind of information always is available to the participants in different ways. And this says getting information specifically for academia who have access to various resources is not really challenging. So therefore, I more often keep my talks independent of whether it is keynote or invited or as a part of other activities in the form of sharing experience and starting always from basic principles, because this is something always we carry with us. That is something that always gives us the strength. Therefore, I share that experience, which is unique. So therefore, that experience you cannot find any resource from net or anywhere. But you find the published papers, that's true. But how it has been approached, how it has started, what are the basic principles? They are not well explained in the paper because paper is not for that purpose. Sometimes we have books or monographs which really open everything. So therefore, the best resource would be in this regard, I believe, books. But not every project or research becomes a book. We may not get time also for that. So let's talk about what we are talking about it today. So one side is sensing, which is well known to all of you. So we sense a parameter from environment. So here I'm not showing the data and the parameters or quantities, physical quantities, information. I'm not showing anything about that. It could be anything. But we need to do some kind of processing on that. What we get from a sensor, which is an interface between nature or the environment from which we are sensing or measuring a parameter, in fact, sensing and measurement are related, is not really under our control. So we need to have various kind of processing. This processing doesn't mean digital signal processing. This means that even removing noise from an analog signal is a processing by an analog circuit. So it doesn't mean really it is done on a processor. It's a generic process. But this generic processing can be done at the hardware level, software level, and it can be in a formal way or brain-inspired way. So therefore, I have just summarized it this way to avoid, putting too many things here. And then at the end of the day, based on the processing, some operation or decision making will come, which is not the topic right now. And for all of them, energy-aware design is now a requirement, because we are talking about these days about the Industry 4.0, how objects can exchange information with each other the same way we exchange information through internet with each other. So the same way now objects will interact with each other, and therefore these objects are not always connected to an electricity wire, which is not possible even. So therefore we need to have all these designs to be energy aware. And anyway, energy is one of the important aspects today, and it cannot be ignored. So, because I'm talking about a domain which includes analog and mixed signals, so I thought I just keep one simple flow, which is very important for us. And more often in this flow, 1 and 2 are missing. And it's not like it is forgotten, it is because it's not given enough time. And this is very important. I want really to convey always this message when I give a talk, that learning should start from basic principles and analysis. So students really need to do analysis, and analysis doesn't mean simulation. Simulation, as you can see, is step 3. If you want really as an engineer to learn, you never forget pen and paper. Nothing better than really analysis by yourself. This will help you to learn a lot. And this helps you also to increase depth of your understanding. So basic principles, basic theorems, and the analysis on top of that are very important. In circuit design also we have the same thing. We have basic principles and in fact science around different configurations. So therefore we need to do analysis based on them to learn really well. And by having that step 1 done, then we can go into basic circuit design analysis. So one is analysis for learning and coming up with some ideas, and then doing the basic circuit design and still analyze it. Still, this is manual with some basic and approximate modeling, which is absolutely fine. Really, you never have pure simulation. If you have pure simulation, I recommend you never do that. Always start from step 1 and 2. When you reach to step 3, yes, then you will start simulating your basic design. And then there you have a lot of scope for really including more complexity by adding non-idealities and see the actual results. And this may continue. In fact, step 1 to 3 may continue as redesign and analysis, because it may not succeed. So you go back, you make your basic model stronger, you analyze again, you redesign, and again you simulate. And if you succeed, then you go to step 5, which is simulation and pre-layout validations. When you have that, then now you will move to the layout and post-layout plus package model simulations. I'm talking about the case when you have the ASIC design, or you have a case that eventually your design needs to be packaged and you have extra connections which create a packaging model, and then you need to include the parasitic effect of those connections and the package itself. This is of course very common in all packaged ICs. Now here, if there is a failure by including post-layout parasitic effects and package, then you will go back even to step 1 and 2, and you want to redesign, because you may go back actually to the step 4, which could be also fine, but for that also you need to have that basic understanding of how parasitic effects affect the circuit. Therefore, you may go back and then make your basic learning model to include parasitic and then move on again. So now this helps you always a lot to really, no matter whether you are in industry or in a research domain, to have a systematic at the same time knowledge-based engineering practice. So I want to give you 3 examples, and these examples, with a limited time, I'm not able really to go into details, but always I start from the basic principles. These are based on our recent research, and therefore you would be able to get also a sense of these activities. With respect to the block diagram I showed you, energy-aware design is very important. And therefore, when we design, we make everything low power. We try to eventually make everything low power or low energy, depending on the design itself and the application. But it's not only energy-aware design or power-aware design. It's also about how we can generate energy from sources available in the ambient. And that's why one of the sources of the energy, which is of interest but has its own complexities and challenges, is the topic of discussion here. Because one thing which is more challenging becomes eventually the topic of research. Those which are straightforward, they can be implemented straightforward. So here we are talking about the inductive rectifier-based piezo energy harvesting using recursive pre-charge and accumulation operation. So you can find details of our published paper this year in IEEE JSSC. But I want to take you quickly through this journey. So everything starts with understanding the application. So therefore, we look at the generic flow of signal in sensor nodes and the generic block diagram. So you have a sensor in a system. You have analog front end, A to D conversion, digital processing, and you will have a DAC and then transmitter, which will send the information. Now you may also have the information which is received, given to an ADC, go back to digital processor, give it back to the DAC, to analog front end, and control an actuator. So therefore, this is very much now is becoming one of the aspects of the IoT systems. And therefore, you don't sense and transmit, you also receive commands for actuation or operation or correction. So therefore, this is a bidirectional path. Now, if you look at the typical power dissipation profile, in this kind of nodes, it's not really uniform with respect to time. It depends what is happening in the sensor node. For example, is it in idle state, doesn't do anything? Is it in a wake-up state, is eventually getting activated? Is it in sensing state, processing, or transmission? Now there are numbers from 1 to 5, and you can see just a sketch of corresponding power dissipation with respect to them, and relatively the time which is spent for them. For example, wake-up is relatively short, while sensing could be longer. Processing could be short, while transmission is even shorter. But transmission can eventually dissipate a lot of power. And idle time is low, time is long, very, very long time. Say, for example, could be 90% of the time. But power dissipation is very low. For example, here, as an example, active time could be around 100 milliseconds, including wake-up, sensing, processing, and transmission, while idle time is around 10 seconds. So it is 0.1 upon 10. So it's eventually 1%. So 99% of the time system is idle. And that's why leakage current also is important. So there are different sources of energy. But when we talk about energy harvesting, really we don't mean to remove battery. Actually, it's most of the cases, it's good to have the battery as long as the lightweight batteries and type of battery is compatible with the requirements of the sensor node. But by having energy harvesting on top of that, the battery life will be prolonged. So the case that we are talking about, the transducer here, is the piezoelectric transducer. I believe all of you or many of you are familiar already with that. So eventually is the mechanical strain which is converted to electrical charge in a simple way. And the equivalent model, electrical model for that is shown here. So there is a current source because it's the charge storage and charge generation. Actually, you have a capacitor. That means even if you don't have any load, so still you will have the generated charge. So that's why the capacitor model will be there. It will have internal losses, which will be modeled by an output resistance. So that's the simple model of the piezoelectric transducer. And to know typical values, for example, open circuit voltage could be as low as 0.5 volt or as high as 5 volt, depends on the amplitude of this mechanical strain. Effective capacitance of the available transducers is some number between 10 to 100 nanofarad. The resonance frequency they have is a number between 10 hertz to 1 kilohertz. And effective loss, which is modeled by the resistor, is a number between 100 kilo ohm to 10 mega ohm. And the Q factor, which is also related to R, is a number between 20 to 100. And effectively, you will see more often a single tone, though in considering non-idealities, it's not really a single tone. So you will get a voltage, eventually open circuit voltage. If it is a single tone, you will see a sine wave. And the current, which is the actual current, which is generated, which eventually variation of charges with the mechanical strain, is the sine wave. So therefore, that means that you need also to consider that excitation to be of this compatible and matching with the transducer resonance, natural resonance frequency. That will give you the maximum power transfer. But it doesn't mean that you cannot operate it at other frequencies, but the efficiency will be low. So here is, as I told you, basic principles are very important. One of the ways to use this transducer is to actually use a diode bridge rectifier and get eventually a rectified voltage at the output, which can be filtered also by a large capacitor, and then eventually get a DC voltage. That's the requirement. But there are limitations. One of the limitations is that these diodes are not ideal, therefore there will be a voltage drop across the diodes. The second thing is that this capacitor and current source actually exchange the charge with each other. Therefore, it's not really like whatever charge is produced always is fully transferred from left to right. We have also transfer of charge from right to left. So therefore, we don't have really 100%, even if you go with ideal diodes, transfer of the energy. In fact, it can be shown that the output power maximum can reach to CV, CV square F is a very well-known term in digital circuits also. This is eventually all about the charging and discharging a capacitor. Even if you assume that the diode drop is negligible, so it maximum will be capacitor of the transducer, open circuit voltage square, and the frequency of the transducer. So now, can we do something better to eventually avoid these limitations of the diode-based rectifier? So here the idea is, let's remove the diode and replace it with an inductor. And this is something called inductive rectification. So what does that mean? It means that if you look at this one cycle of the piezoelectric resonance, so this is the ideal model, without any loss, without any load. So eventually this capacitor is getting charged and discharged with this ideal current source. So let's assume we are in the first cycle where IPZ is positive. So therefore the capacitor is eventually getting charged till current reaches to zero. At the zero crossing, voltage is maximum and current is zero, which is typical of a capacitor behavior. But after the current goes negative, so capacitor will be discharged. So we don't want to avoid, we want to avoid that. We want to, now when we have the maximum voltage on the capacitor, which is maximum stored charge, we want to transfer it to load. So therefore, this is what can happen. Assume that you put an inductor using switches across the capacitor, and this inductor is in such a way that the LC resonance frequency is much higher than the resonance frequency of the transducer. In other words, the period of the oscillation of this LC is very small as compared to TPZ, which is the period of resonance of the transducer. Therefore, really, transducer will not, you will not see this effect very clearly at the output of transducer. It's a very short instant of time. So now you know that if you connect an inductor which doesn't have any initial flux across a capacitor which is already charged, so this charge eventually starts flowing through the inductor in the form of a current, and the inductor eventually starts getting charged. That's why the current of the inductor suddenly ramps, and in fact if you stretch the scale, it will show this kind of behavior. And the capacitor eventually will get discharged in the inductor. That is exchange of the inductor-capacitor energy in the LC circuit, till voltage across capacitor reaches to zero. So now we have eventually transferred the energy to the inductor. So now no energy in the capacitor, but energy which is in the form of the magnetic form. So that is maximum now in the, so the magnetic flux is maximum in the inductor, and the current reaches to its maximum value. And then we will go to the next step, which actually we want now to transfer this energy to the load. And this is what we do even in the DC to DC converters. So therefore now the current through inductor is actually charging, say, output capacitor or the storage element or battery or anything else, or directly given to the load, but more often directly is not given. So here eventually you consider it some load at the output. So this is a very interesting approach, because you can actually apply this technique and then effectively transfer, ideally, of course, transfer the entire energy to the load. And then as inductor transfers the current to the load, so naturally it gets discharged, and the output current also first increases because load is connected to the inductor. It jumps abruptly to the IL max, and then it drops to zero as the IL drops to zero. Therefore, we will eventually get a transfer of energy using this inductor. So here you see there is a lot of many switchings are involved. So to see how the waveform will be, for example, if you have a sine wave, single tone, and then every half cycle you do this, so eventually you charge and then discharge. So every cross point shows, every cross here shows the transfer of energy to the load. So every half cycle, energy is transferred. One is positive, one is negative. Therefore, during switching, we use the right polarity to be able to always charge the output capacitor, for example, or load capacitor in one direction. So therefore, you will get this kind of waveform at the output of the transducer. And here there is no diode. And the current which goes to the load has that kind of triangular waveform, which are actually spikes. This is extended scale to be able to see it, because frequency is very low as compared to the frequency of the transducer. We can have it instead of every half cycle, we can have it one cycle. So if we do it one cycle, that means that we are actually allowing the inductor to even get charged to the negative current. And then again, repeat the same thing by changing or flipping the polarity and then transfer. So this way we would be able actually to get double of the voltage, open circuit voltage we get in the previous case. Because ideally, if you allow this current to continue, dropping in the inductor, so inductor should be able to give you almost same value of voltage that it was giving with the maximum current, and then till the current reaches to zero. So if you go with the comparison of the two cases, in case one, so you will get eventually CV square, right, F. So the energy which is eventually you get is 1 upon 2 CV square. So it will be 2 VPZ square. In the case of B, which is eventually 1 every cycle transfer, so you will get 4 times. So as far as energy is concerned, so this is 4 and this is 60. That means 4 times more energy. So therefore it seems that the second one will give a better option for energy transfer. So therefore we used the same idea, which was not new, but what we did, we actually came up with a method which is based on initial eventually charging to even increase this voltage further. So there is an initial charging, but it is done every few cycles. Number of cycles is not fixed and depends on because if you don't transfer to the load and continue this cycle of charging and discharging to the inductor, you actually would be able to increase the voltage further and further. But finally, we reach to some level where the devices will break. Therefore, we limit it to the breakdown voltage of the technology. Devices in that particular technology. In the 180 nanometer that we designed, we used 3.3 volt devices. So Vmax for us was 3.3 volt. And then we use a circuit which will detect when voltage is approaching to Vmax. Therefore, it dynamically decides when to stop it. A number of cycles are determined by that. So if you compare theoretically, the proposed method, which is the blue one, eventually is able to overcome all other methods with respect to the efficiency. And efficiency eventually, or I would say not efficiency, eventually power transfer. Figure of merit, which is the output power divided by output power. If we would have used a full bridge rectifier, that is the figure of merit. So theoretically, you can get a number between, say, around 12 to 13 times up to around 20 to 23 times of a full bridge rectifier. And of course, if the output voltage increases, naturally, we would be able to get more energy. And this is just an idea of what was actually on the chip. On the chip, we had many switches, and these switches were exposed to high voltage. Therefore, we had really a tough time to overcome the problems of the breakdown and make sure that nowhere no voltage will be negative and nothing will break. And just to share the experience, actually our first tape out had problem in part of the circuit. Then PN junction diodes of the source and drain with the bulk, they were creating problem because of the turning on, and also because they were eventually, and specifically within a well, by the way, within a well. So PN junction and then bulk of transistor, which is within a well. So this was one of the problems, and then this was identified after fabrication. We missed it. You know, the flow that I told you, in spite of having through that flow, but that part was missed because it was a parasitic diode, and then we didn't investigate it deeply during simulation. Next time we actually investigated all parasitic diodes, and then in the second tape out, then we got everything right. And what you see eventually as dotted line is the entire switching circuit, and transducer is here. So the entire power stage is on the chip. So everything is on the chip. Inductor is not on the chip. So there are too many switches and too many eventually states, and you can imagine that how much precise we need to be to make sure that all timings are generated internally properly. So eventually it starts with the integration, as I showed you before. And then here, because we are going with after a few cycles, not really half a cycle, so therefore voltage can also go negative. But for every node, we make sure that the node voltages don't go negative, because as I told you, then we may have problem with PN junction diodes. Therefore, we take care of it by connecting left and right side of the piezo transducer by a resistor to ground in switching states. And this operation eventually gives the rectification we need, because we control the polarity of the current through inductor to be always in the direction that we need to give it to the load. And if we want to really energize the inductor also, we have put that option. And the reason is because in our experiment, we actually had a storage element. And the storage element was a very large capacitor as compared to the output capacitance of the transducer. Therefore, effectively, it can hold a lot of charge on it. Therefore, it can be also used to energize the inductor. So we use these two eventually new features which didn't exist in the previous works, and then we were able to achieve the performance which was better compared to the reported works. I show you the table, but before that I want to show you the entire chip and the PhD scholar Siva, who actually worked a lot on this chip. This is his second chip. So he actually made this setup in the lab during COVID time, where he was eventually working in the lab alone. And only we had, of course, limited interactions because of COVID rules, but we were eventually, it was only 2 hours effectively at that time. But he took eventually a shaker from one of my colleagues from civil department, and he was able to mount the IC, our ASIC, which was packaging QFN64 on a PCB, and put it on the shaker. And then he had source meters to measure the currents, and therefore he will be able to measure the power, and then observe the waveforms on the DSO and save them. So the measurement results are shown here. And then here I want to show you how results could be different with respect to the theory. So if you look here, for example, there are some losses. For example, when the voltage eventually, when we look at the two sides of the piezoelectric transducer, we expect the voltage to jump. Say here, because we were discussing about 3 volt, 3.3 volt actually was the Vmax. So we expect to reach to 3 volt after a maximum number of cycles before zero crossing Vmax detector detected. But we had around 800 millivolt loss. And this time, as I told you, so effectively it is a time which gets to reach to Vmax. For example, theoretically, it was 5.6 milliseconds. With post-layout simulations at SS corner, slow corner, which is the slowest, was 6.8 milliseconds. But actually, when we measured it, this was a number between 8.4 to 9 milliseconds across a couple of chips. So this 800 millivolt naturally reduced the energy that we expected to be transferred to the output, but this is coming actually from the some of the losses that eventually are quite different when you have the real world measurements as compared to this even post layout simulation. So one was the inductor losses itself, and one was the losses of the transducer. So naturally it will have effect. Another source of loss is that when we have the switching. So we assume switching happening, all switches eventually switch in a negligible time, but practically it's not the case. Therefore, delay in the switching of the switches naturally results in the loss of energy from the inductor and the capacitor. So, and here is a demonstration to see that how if really you have different values of the effective resistance will have the impact on the transferred power. So, for example, here you consider two cases. One case is we have a smaller inductor, 47 microhenry, with effective resistance of 0.5 ohm. The other one is 10 times more, 470 microhenry, which naturally the effective resistance increases. So you can see that with increasing the inductor, because the effective L has increased, so we get a better extracted power at the output, even though the effective resistance is slightly more. So eventually the conclusion was if we increase the effective value of the inductor, provided we have the relatively accurate zero crossing detector so that the inductor can be switched quickly, that zero crossing inductor also is on the chip, the overall losses will reduce, and the power transfer to the output depends also on how much is the open circuit voltage. Open circuit voltage, say at 1 volt, results to more than 21 microwatt power transfer to the output. And naturally, if we have the less loss within the resonator, which is here based on the values from 1 mega ohm to 6 mega ohm emulated. So naturally the transfer power to the output will increase. And then of course, after 6 mega ohm is almost like saturated. So it reaches to the vicinity of 20 kilo ohm. So now going to the comparison. So one thing that we had is that everything in this design was self-timed because we had zero crossing detector and Vmax detector. Therefore, the number of cycles are actually defined based on the Vmax. And this is where we had yes as compared to other no's. So this is always reaching to the maximum swing depending on the Vmax. It's completely self-timed and natural and effective because we are checking for reaching to the Vmax while other techniques don't. Therefore, we don't depend on the initial voltage, which is pre-charged eventually value of the inductor. So measured, of course, figure of merit is not as high as what we observed from theory because of losses, but relatively still it is high. So therefore, if you replace it with the diodes, even with ideal diodes, of course, so you get more than 3 times energy transfer at 2 levels, which is tested. So the second part that I want to talk about, now we talk about energy harvesting. The second part is about sensing itself. Now, see, imagine that you want to effectively have all of them on a single unit on a sensor node. Therefore, another part which is important is how accurate you can have a sensor node, because more often we think that sensor nodes may not be accurate, and accuracy comes only in the lab with sophisticated measurement instruments. So that's not true always. Specifically, when we talk about sensor nodes, the quantity which is measured, for example, here we are talking about resistive sensors, may have a very wide range. It's very difficult to limit it always. It's coming from ambient, it's coming from the place that the sensor is installed on it. So therefore, it's very difficult to control everything. It's another lab environment. So we need to look at also wide dynamic range of this resistor sensor. We need also to be conscious about the accuracy. So accuracy we had in mind was 100 ppm, but actually we could achieve below that. And at the same time, we don't want any user to be, or an engineer next to that sensor. No, that's not also possible. So therefore, it should be completely auto-calibrated. Everything needs to be done automatically at that system. So these are all remote. So this is another work that is published in 2020, another JSSC paper, but it's focused on how you can achieve this auto-calibration with a wide resistive range of the sensor, but at the same time achieve the accuracy. So here also, we first look at the problem. We try to go with the basic principles, understand the problem, and then try to get the results out of it. So now one thing we want to know is, what is the problem? Problem is that, first of all, we want to measure variation in the value of a resistive sensor. And even we don't know what is the initial value of sensor. When you are in the lab, you measure. But when you are not in the lab, you don't know. Even what is the value of sensor, even if there is no effect of that excitation which is coming due to the external parameter. So it's not eventually exposed to any parameter. So even initial value is not known to us. So we want to measure delta R. Of course, we are not interested to measure the base value. We want to measure variation of that, variation or deviation from base value. Range was high. It's like from a few kilo ohm to hundreds of kilo ohm. So it's relatively high. And we want to achieve accuracy in the measurements as low as 100 ppm. And RS also is not constant even. Not only it's not known, it's not even constant. So therefore, you can imagine that the most complex problem, and we want auto-calibrated, everything we want to be automated, the entire measurement process. So we went with two methods to, when you start from basic principles, start from what is already available. So one is Wheatstone bridge, which is very well known method, and one is another method which is based on our past eventually published paper at the system level, which is eventually current excitation bridge. We call it half bridge, half resistive bridge, and we use current sources. So we did the analysis, just as simple as I told you, pen and paper analysis, to see that what are the differences between Wheatstone bridge and current excitation bridge. If we assume that we have a value of delta R by RS change in the two cases, and the supply is VDD for the case of Wheatstone bridge, for the case of current excitation, current amplitude is IDD. So we wanted to understand that now what are the differences between the two cases. There are different parameters. How much would be the magnitude of output voltage? How much would be the sensitivity? That means how much output voltage changes for a given percentage of change in the sensor. How much would be the power supply rejection ratio, because it has impact. If supply has noise, how much it will have impact on the measurement. And then what are eventually a parameter which is K, which is a design parameter. So in the Wheatstone bridge, for example, is ratio of the corresponding resistors. In the current excitation half bridge, it's eventually ratio of the output impedance of current source with the base resistance of the sensor. So what would be the maximum sensitivity, which more often maximum sensitivity is happening at the quiescent point. Here quiescent point is when delta R by R is 0, that means at base. And then how much would be then when delta R by R is maximum? And current consumption and eventually sensitivity for 3 different base resistors. So this is also important because sensitivity itself may change with the value of the resistor. So these graphs are actually plotted based on those expressions. And as you can see, for example, current excitation is much better with respect to linearity compared to Wheatstone bridge. And sensitivity, if you normalize it to VDD, it is constant across all variations of delta R by R. We are going from minus 100% to plus 100%. That's a wide range of variation. And PSRR across the wide range of variation. So overall, you can see that the current excitation bridge wins because when you have the current source, intuitively also is expected. So you are eventually shielding the supply. shielding the sensor and the circuit from the supply by putting a current source in between. So therefore we chose that, and then we continued with the design. So now on the left, you see the current sources, which are square current sources for the ease of the design. We used square current sources rather than sine wave. And then we have an instrumentation amplifier. We use chopper modulation. And therefore we need filtering after that. And then after that, we will give it to a digital filter as well. So therefore, the main part of the circuit is here. And variation of this RS with respect to the initial value, and considering we have an RF, is eventually using that chopper or demodulator gets converted into a DC value which is measured. So this DC value eventually is proportional to delta R, not delta R by R, by the way. It's proportional to delta R because we are using current. In Wheatstone bridge is delta R by R. And there are so many factors which are contributing to non-idealities. So how RF is close to RS? You cannot match them. You don't know even RS. So therefore, there is a mismatch. Current sources may have mismatch. Even you may not have an ideal square wave. In fact, it's trapezoid because Roissam and fall time are not zero. There are parasitic capacitors. There is interference. So these are all the bottlenecks that we need to deal with if really we want to achieve 100 ppm resolution. So therefore, we cannot have a very high frequency of this current source because otherwise parasitic capacitors will be a problem. And then if we make it very low frequency, then we will not get advantage of the chopper modulation, which increases SNR. So therefore, we had to come up with a kind of trade-off between the two values. So we decided eventually what to do is that to go with two frequencies. One frequency, we call it a slow clock, one frequency, fast clock. So when it comes to the current sources, we use a slow clock to effect of parasitic capacitors go away. When it comes to the chopper modulation, fast clock. And then how to make it automated, because it is assumed that there is no engineer or anybody who can access this board, and this is placed somewhere remotely. So therefore, it should be able to have this automated flow using a controller sitting next to this ASIC. I'm not showing the internal circuitry because unnecessarily it will divert your attention. Main thing is about what is around this ASIC. So first, we maximize the sensitivity automatically. So what this actually controller will do, it will send signals for various controls. For example, we have auto programming control, which controls the value of RF. It's a digipod. We have the switches, which are controlled by another signal, which is eventually switch control from controller. We have also amplitude adjust control, which is for the current sources, which are injected into the sensor. Then we have to, first we maximize the sensitivity. In fact, the system does, no user. Then system eventually will measure the baseline resistor. System will do offset calibration, and then system will do delta R measurement. So it's a 4 phases operation. First part is straightforward. It's just the polarity based to get the maximum sensitivity. But actually the operation needs to be completely standalone. So therefore, the program for that is written already in the controller. It's like a state machine. On-chip blocks also, as you can see, are not very complicated. In fact, one of the features of this work is simplicity. Simplicity is always good because it will give you the best of depth that you can achieve. And also, when you need accuracy, more complexity brings more sources of error. So we use dynamic element matching for current source on the chip. So this was one way to overcome the offset or mismatch between current sources. Then we had 2 clocks. One clock was for the slow clock for current sources and fast clock for the chopper modulators, as you can see here. At the final output, because we had to take both of them, so therefore we used as an XOR ignore. So it's actually a very simple circuit, but it combines the two frequencies. It's like behaves like a multiplier, and then gives us the output, and the output will be filtered, and the DC value will be extracted. Now, one interesting point is, so these are the phases. I don't go into the details. One interesting point is that what we have is actually differential ratiometric output. Why? Because these values are actually recorded in the microcontroller. Delta R is eventually the parameter we want to measure. Delta Rm, which is shown by red color, is actually the mismatch or deviation between the RF and R base. Then we have still slight components of mismatch. So this eventually gives an equation. And then if you solve this equation effectively, which are obtained eventually numerator, in phase 3, we actually measure the offset. So therefore, this we deduct it from the measured value in phase 4, and what remains is only delta R by Rs. So therefore, this part is calculated within the controller. So therefore, we are able to achieve delta R by Rs. Now, by having that, even though theoretically we were looking at 100 ppm, but actually we ended up better than that. Other components, of course, is an instrumentation amplifier, which is a current mode instrumentation amplifier. Here you can see the waveforms. When you chop the waveforms, so it looks like a modulated waveform. This is very good technique for increasing signal to noise ratio by eventually modulating the signal to higher frequencies. It's like up conversion, but noise will remain into the low frequency band because noise is at the input of the INA after the switch. So therefore, after up converter. So therefore, when we do the demodulation, noise will go to the higher frequencies, but signal will go back to low frequency. And then we use low pass filtering. So this is a very well-known technique, which is called chopper modulation or chopping modulation for reducing the noise and increasing signal to noise ratio. So this eventually noise floor, not only we reduce low frequency noise, but also noise floor also drastically reduced by a factor proportional to the square root of modulation frequency to the chopping frequency. So eventually, chopping to modulation is the reduction factor. So if you multiply by square root of modulation to chopper, so that will reduce. So in fact, the RMS value, noise floor was around 200 nanovolt per square root hertz. It would drop to almost like less than 25 nanovolt per square root hertz. And that was the reason we could increase the signal to noise ratio drastically. For modulation, we use low frequency, 100 hertz, to reduce parasitic effects, and chopping frequency was 10 kilohertz. So here is the summary of actually these phases. So for maximum sensitivity, we use a polarity checking. For the RS measurement, which is the second phase, we actually use a digiport to be able to measure the RS. Then we do the offset calibration, and then final stage is delta R measurement. So when we want to do offset calibration, we don't expose the sensor to, a sensor is not exposed to the external factor, or what we call actually, we call the conditions at which, for example, if it is temperature, we consider a base temperature. So at that base temperature, this offset is calibrated, and then delta R measurement now will be performed. This delta R measurement now can be done at any condition. And then we just do the division in using the controller and get the results, which is delta R by RS. So here is some of the details of the current sources. There also we actually use I use an idea to have a kind of floating current mirror, and this will help us to simplify the circuit and achieve really very high output impedance current sources. And we had 3 kinds of current sources: coarse, medium, and fine, for adjusting values. These values are eventually controlled. These switches, which are used for the value control, are controlled by this auto amplitude adjust control, which is coming from controller. So range we used for adjustment was around 100 nanoampere to 44.4 microampere, because range of the base resistor was very high, sensor resistance. Therefore, we needed to keep the range of the input voltage, common mode as well as differential mode, compatible with the range at the input of the INS, specifically common mode. That's why when the resistor increases, our ref also will increase, but we have to reduce the current so that the effective common mode voltage will not be very high. So here it eventually shows that how the flicker noise also drops without and with chopping. So which is very well known eventually fact. It's not new, it's very well known because of the upward modulation. It is eventually happening because of the signal will go to one band and noise will be another band. Therefore, you can do nicely filter and then get the noise power reduced. So therefore, we could reduce the flicker noise. We could take care of the offset and mismatches. We could take care of the wide range of resistor with a programmable current source, which is automatically programmed. So we put all of them on a single chip. So this is the full ASIC, and then on a single chip, single ASIC, and then put it on the board. And this is the controller which has that program and then does everything. And the connector for the sensor. Sensor even can be a different wide type of sensor. So it can be anything. So we got eventually one sensor from our collaborators for just doing a measurement with their sensor, which was completely, unknown to us, to make it really a scenario where we don't know anything about the sensor. And they sent it to us, they shipped it to us. And we also did it with the typical passive resistors. And of course, this is a plot which just show that, for example, even parasitic capacitor increases to 56 picofarad, still we are able to achieve delta R by R in ppm. Measurement, which is very low value, to as high as, for example, beyond 1,500 ppm. So it's a wide range of variation. We tested that sensor that we had, resistive sensor, with respect to its deflection and the delta R by RS that it shows. And as you can see, we have our system. Eventually, we did 3 times measurement with LCR meter, and compared with eventually the commercial measurement system. But to get exactly the numbers are actually summarized over here. See, base resistance, we changed from 1 kilo ohm to 500 kilo ohm, which was really large as compared to all reported works. Then, as a result, we had to change the current source range from 100 nanoampere to around 44 microampere. Maximum delta R by R that we can measure is plus minus 135% if base resistance is minimum. If base resistance is maximum, it's plus minus 120%. And minimum value, interestingly, for low value of RS goes as low as 26 ppm, which happens at the maximum current, and goes to 72 ppm at maximum RS. CMRR is for INA is very important, is more than 110 dB. Sensitivity is programmable, and it does auto-calibration, while none of them does. Reported works does the auto-calibration, except the last one. But if you look at the last one, it eventually has a fixed 100 ohm resistor. So therefore, it's not a very challenging task to have the auto-calibration. And we are able also to mitigate eventually thermoelectric effect, because we are not using Wheatstone bridge. Wheatstone bridge has metallic junctions, and that may create the EMF eventually effect, which creates the drift in the measured DC value. And parasitic consideration is not reported really for any of the reported works. So that means they don't consider it, but we have considered that. And finally, the last one, which is the recent work, very recent work published in August 2022, I talked about the computation and processing. So here, is a narrow ASIC, which is really low power, extremely low energy. And all these numbers that I told you are with respect to the closest numbers worldwide reported. So it's eventually a liquid state machine, which is a simple kind of neural network. We have kept 36 spiking neurons, a very small number, because this was the first tape out in this technology with respect to this application, which is 45 nanometer SOI. In the other two works was 180 nanometer CMOS technology. This is 45 nanometer SOI technology. And the reason was because we are using a specific effect, which is called band-to-band tunneling in this technology. But I want to show you mainly the overall view of this work. So this is called eventually liquid state machine, which is a kind of recurrent spiking neural network. And the application is for speech, eventually classification. And here, effectively, you receive eventually spikes which are generated from the ear model. And then at the output, you will have the classification. So what we have on the ASIC right now is actually the spiking neural network and synapses. So to see the actual circuit is a circuit similar to what I have shown on the right side, we have shown. So this circuit is eventually a leaky integrate and fire neuron with several inputs which are received from the synapses and other neurons. So these neurons are eventually connected to each other in a random fashion, practically. And we kept weights constant, as uniform across all, but programmable from offset. So eventually what happens is that we receive the signal in the digital form, this speech signal. So there is a digital to spike converter which generates spikes. So because this is a spiking neural network, so it receives the spikes. And then this eventually synaptic array, which is eventually embedded within this recurrent SNN or liquid state machine, will generate the spikes, and this spikes will be decoded back into different classes by an output stage. And these classes eventually will tell what is the spoken word. So, and this output stage right now is not on the chip. So therefore it receives the pulses and it generates the classes, but it can be kept on the chip. So these are not challenging part. The main challenging part was actually the main network here that we had to really simulate. And then, not everything also, it was specifically band-to-band tunneling. We were not sure whether it is taken care in the PDK. The reason is because this is a region where almost like transistors are off, like deep subthreshold, and therefore we were not sure about operation. But interestingly, that those simulations actually were realistic in the sense that we observed the band-to-band tunneling after measurement. So to do the measurement, eventually we had to generate these spikes and the digital inputs, all using an FPGA board, and then give it to the chip. And then on the chip, we have 36 neurons and 256 synapses. And what you see effectively, these are all like a kind of, if you look at these neurons, for example, for each neuron, you'd see a pattern of a spiking as a function of time. Suppose this is for word 0. So that you see this pattern of spiking. And then for the output, after passing through the network, you see this pattern of spiking from the network. And these are, of course, captured experimentally. So it's a very small kind of, neural network, and it's extremely small. Therefore, if you look at its behavior with respect to the ideal case, it still is able to, follow the ideal case behavior, though classification error is not as good as the ideal case, because in ideal case, as I told you, we had a model, and this model eventually was embedded into the PDK for the band-to-band tunneling. So therefore, we didn't have really an idea of how much accurate it would be. Therefore, after measurement, we observed more error, but still, as you can see, it follows the simulation, which was based on the ideal leaky integrate fire model of the neuron. And number of classes, of course, are not very high at this moment because there are only 36 neurons, but it's a promising approach. And this is the setup. Main setup is eventually FPGA, ASIC, and the DSO to see the spikes, but they are also captured, of course. And then they are transferred into MATLAB program for the demonstration purpose. Because when we speak, the same is actually displayed on the display so that we know what we have spoken. And then what system recognizes, that also will be displayed on the monitor to see whether they are same or not. So this is eventually has the minimum static power, which is reported worldwide. It's really very small, just 2.7 picowatt, which is very small. And energy per spike also is very low and compatible with one of the latest recent, reported works. But if you look, that area consumed for that is around 2,800 micrometer square. For us is 40. And the main reason is because the neuron itself is a very small neuron. It has a very small number of transistors because we don't make really a complete integrator. We actually use the bulk of transistor as a charge storage. And this band-to-band tunneling is eventually happening, allowing to discharge the neuron. So therefore, this leaky integrate and fire neuron can be easily implemented using a limited number of transistors, so area will reduce. So overall, I just wanted to give you the glimpse of the three works. And this is in line exactly with the directions we need to have for the sensor nodes. Ideally, we would like to have this kind of processing, ideally ambitious kind of science fiction on the sensor node in edge computing. Lot of processing is expected to happen at the node before important information are transmitted outside, because now there is a lot of problem with the cloud access, going to the cloud, getting the processing done, going back. And this also results in the exchange of a lot of data, and the bandwidth is limited. So there is a limitation on the available frequency bands, number of nodes are increasing. So eventually there is a kind of exponential increase. So for edge computing also is finding its own place and demand more and more. And one interesting thing here is that if these unknown features of devices are explored, and this needs really collaboration between device and technology researchers and circuit and system researchers, which happened in this work. My colleague, Professor Udayan Ganguly, actually his group had worked on this band-to-band tunneling effect in SY devices, and we could take advantage of that work and then bring it to the circuit level. And that's why standby power is really extremely low as compared to the other methods, if we consider same level of area and consumption of energy. And if we consider same area with respect to other works, energy and standby power is almost 5,000 times less. So therefore, it's a kind of unique results reported. So this, of course, needs many PhD scholars involved. For example, first work was Siva. He is right now in Mediatek, Taiwan. The second work was Miraj Ahmad. So he is right now a research associate in UK. Then we have the last work, which is Ajay and Vivek. Ajay was my PhD scholar and is graduating. And Vivek also is graduating, who is Udayan's student. So eventually we had to make a team. and both of them are graduating, and in addition to the PhD scholars and PhD students, and time, which is very important, facilities are important. Therefore, the support for the tools coming under METI support under the scheme of SMDP C2S program, and also fellowship of students. Some of them came from DST. Then we have LSI lab for the design and embedded system lab and ISL. I have not written here, but eventually that lab also is used for the testing and measurements. So Global Foundry supported us for 45 nanometer tape out. Europractice eventually for providing service for both 45 nanometer and 180 nanometer. And CIVO was in CTU Taiwan, NYCU, with Professor Chen, my collaborator for some time. And then he used this facility. In fact, this inductive rectifier is a joint work with him. And CIVO eventually did a first part of the work over there, but then the second part of the work and the second ASIC and testing was done here because of the COVID. Eventually, everything moved to us because he was not able to travel. So that's it, and this is the end of my presentation.